Hi everyone, this is MathsForUni. This is question 9 from lecture 10 of our Udemy course, Bridging the Gap to Maths at University. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, find real numbers a, b, and c such that both of the equations 4a squared plus 16b squared plus 9c squared equals 100 and 6a plus 20b plus 3c is equal to the square root of 3,500. Find a, b, and c such that both of those equations hold. There is a hint that says that the Cauchy Schwarz inequality for the dot product will prove useful. Using the hint, we can frame the equations in terms of dot products. The first equation can be written as the following. So that's this equation here. We can write this as 2a, 4b, 3c dotted with itself on the left-hand side, and then the right-hand side will be 100, because we will have a 4a squared from here, a 16b squared from there, and a 9c squared from there, with a 100 on the right-hand side. Because we have the same vector dotted with itself, we can instead write this as the magnitude of the vector 2a, 4b, 3c as being equal to 10, because this is the magnitude squared, which is equal to 100. This motivates writing the second equation, which is this one here, in terms of a dot product that includes the same vector here. This would be the same vector 2a, 4b, 3c, but then we would dot it with the vector 3 to get 6a, 5 to get 20b, and then 1 to get 3c. And then the right-hand side is the square root of 3,500. Then we have the same vector in terms of a, b, and c appearing in both equations. Following the hint, if we look at the Cauchy Schwarz inequality for the dot product with this equation here, then it says that the modulus of this dot product is less than or equal to the magnitude of the vectors multiplied together. We can then calculate the right-hand side of this inequality, because this here we know from our above equation, this is 10, and then this thing here is just numbers, so we can calculate it directly. This gives us the square root of 3 squared plus 5 squared plus 1 squared, which is 35. And this here gives us a 10, and therefore we have the square root of 3,500. Now that we've written down the Cauchy Schwarz inequality for this dot product equation, we note that this equation here is an equality case for this Cauchy Schwarz inequality here. We know that this only occurs when the vectors involved are parallel to one another. To clarify, this is an equation that we have here, but then if we consider the left-hand side using the Cauchy Schwarz inequality, we recover that it is less than or equal to the same value that appears on the actual right-hand side of our equation. Therefore, these vectors must be parallel because we have an equality case of the Cauchy Schwarz inequality. So we have 2a, 4b, 3c as a vector as being a constant multiple of the vector 3, 5, 1. However, we need the value of lambda to be chosen such that the modulus or magnitude of this vector 2a, 4b, 3c as being equal to 10, in line with the first equation that we have here. This dictates what the value of lambda must be. If we use this equation here and put it into here, then we get that the magnitude of lambda times 3, 5, 1 must be equal to 10, and therefore the magnitude or absolute value of lambda multiplied by root 35 from this vector as we found earlier must be equal to 10. And then this equation here has two solutions for lambda, one positive and one negative. We need lambda to be positive so that then A, B, and C are themselves positive because our original equation must have A, B, and C all being positive, since the alternative is that if lambda is negative, then A, B, and C are all negative, but then we have this plus root 3500 that gives us a contradiction. As such, lambda must be positive, and so we get lambda equals 10 divided by the square root of 35. Then the real number solution for A, B, and C can be found by putting this value of lambda into here. So we get 2a, 4b, 3c as being equal to 10 over root 35, and then the vector 3, 5, 1. Taking the individual components and then dividing by 2, 4, and 3 to get A, B, and C gives us A equals 15 over root 35, B equals 25 over 2 root 35, and C equals 10 over 3 root 35. This is the real number solution to the equations that we had above in our original question. The Cauchy Schwarz inequality ended up being very helpful in this extremely specific case because we had an equality case and then the vectors involved needed to be parallel. If you've enjoyed this content, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.